So we're going to start our discussion of limits with rates of change. So the text calls this section the idea of limits. I'm calling it rates of change. That's what the idea behind the limits that we're going to be looking at is all about. So let's start with rates of change. So the first thing we're going to look at is what's called the average rate of change. A lot of times we'll denote this AROC, average rate of change. So the average rate of change of some function y equals f of x with respect to x over the interval x0, x1 is given by, and now we have a couple of different ways to represent this. Our notation, average rate of change. Now we can calculate it as delta y over delta x, where delta is our standard change. In other words, delta y from x0 to x1 would be y1 minus y0, the later value minus the earlier value. And delta x would be x1 minus x0. Okay, so since y is f of x, we could also write y1 as f of x1 and y2 as f of x0, so we get f of x1 minus f of x0 over x1 minus x0. And that's going to be a very useful calculation quantity for us to use if we're just trying to calculate the average rate of change over some interval. Later on, when we apply this using limits, we're going to look at this last form here, which shows f of x0 plus delta x minus f of x0 over delta x. Now realize this is really the same as the previous form, because if you take f of x0 plus delta x, that would be just f of x0. Now delta x is x1 minus x0, so plus x1 minus x0. And you just get f, with the x0's canceling, of x1. So this first term here is just f of x1 as before, and delta x is precisely just x1 minus x0. So those are the same, but they can be used in different cases. Okay, so one thing I haven't said is we've seen delta y over delta x before as a slope. So this must have something to do with a slope. So let's look graphically. So let's say this is the function y equals f of x. This is a graph of that function. And we're going to talk about 2 points, x0 and x1. So x0 would, at x0 we'd have the point x0 f of x0. And at x1 we'd have x1 f of x1. So now, if we're talking about this quantity we were looking at above, f of x1 minus f of x0 over x1 minus x0, then that would be the slope of a line. That would be the slope of this line, connecting those 2 points. And that's often known as the secant line. All right, so the secant line just connects the 2 points. Now that's not the curve we're looking at, but it's something related to it. And so this secant line, its slope would just be f of x1 minus f of x0 over x1 minus x0, which is just our average rate of change. So what we're seeing is that the average rate of change between 2 points is in fact the slope of the secant line connecting the 2 points. Okay, so that's what we're actually looking at. So this is all about average rate of change. But isn't there a thing called instantaneous rate of change? Which is a funny term in itself, because how do you have an instantaneous rate of change? How do you have something that's changing in an instant? because don't you need some time or some distance over which to change? Well, that's where it's going to be an interesting quantity. And so the definition here will come later. And we'll say a lot more about instantaneous rate of change later. For now, let's just look graphically. So graphically, what are we talking about? Well, now let's just focus in on one point, the x0 point. All right, so now we just have this point here at x0, and what would be the line that we're going to look at? So instead of looking at a secant line, we're now going to look at the tangent line. Okay, so this is going to be the tangent line, the line that just touches at x0. The slope of this line is going to correspond to the instantaneous rate of change, but right now we have no way to get that. We don't have a way of getting a line from one point. What we could do is we could use other points on the curve and use secant lines, maybe ones that get closer and closer, and they seem to be approaching what the slope of that tangent line is, but not exactly. All right, it's just an approximation. So we can approximate instantaneous rate of change using secant lines, which are just average rate of change. Okay, so, well, there must be some connection, and the connection is going to come through limits. So in order to try to get the idea of what we're talking about, sometimes it's good to think about calculus in terms of the physics related to it. So if we're talking about motion, so let's say s of t is some position function. So that just gives the position of some object at time t. S is the position. So if we're going to talk about change of position, well, that's velocity. And your average velocity would be your average rate of change. So your average velocity over some time span, t0 to t1, would be your v average, or in other words, something like s of t1 minus s of t0 over t1 minus t0. Okay, that would be your average rate of change. We could also write that denominator as delta t, but it doesn't really matter. So when you're talking about velocity, so imagine you took a trip in your car and you went 120 miles in 2 hours. Well, that's a change in position of 120. So 120 over 2 change in hours, change in time. So 120 over 2 is 60. So you have 60 miles per hour is your average velocity. So your average velocity over that whole time span would be 60 miles per hour. But that doesn't talk about what happened at any instant. At some instant, the speedometer may have read 70 miles per hour or 65 or 55. So what we're talking about with the average rate of change is the average rate of change over that time span, in this case, average velocity. And we'll have to see how that can then be translated into instantaneous rate of change or instantaneous velocity with limits.